Welcome to the Organic Chemistry video content to accompany Organic Chemistry 1 lecture guide and the Organic Chemistry primer. The problems in this video come from Part 1, Structure, Stability, and Conventions. Our first problem deals with resonance and delocalization energy. We're given a series of ions and asked to produce additional resonance contributors and to draw the resonance hybrid structure for each ion. We'll start out with a cation at the top of the page. Now, if you have a positive charge on a carbon atom, remember that this carbon atom will only have 3 bonds, formal charge of +1, no lone pairs. This is a site to which electrons would be attracted because of the positive charge on the carbon. You can only move pi bonds and lone pairs when drawing resonance contributors, and we have no lone pairs in this structure, so the only option is to move a pi bond which will be pulled towards that positive charge. If we do that, using our resonance arrow, the resulting structure will look like this. We've moved the pi bond to the position between the 2 carbons on the end. We highlight those with these green circles. That leaves the carbon in the middle, which used to have 4 bonds with only 3 bonds, and then that carbon will have a formal charge of +1. Now, if we were to move these electrons back that way, we would go back to the original contributor we had already drawn, but there's this other pi bond over here, which we can also pull towards that cationic carbon in the same way we did with the first structure, and that will give us a structure that looks like this. Those are all the resonance contributors that we can draw for this structure, and now we're asked to assemble a resonance hybrid from these. To begin the process of drawing the hybrid, we start out by drawing all the sigma bonds that were in the structure. We ignore the double bonds and the charges for the moment. Now we fill in any places that have a double bond in only some of the structures as dashed lines. So if we have a double bond in some of the contributors in this spot, we put a dashed line there. Some of the contributors have a double bond in this spot, some have a double bond here, and some have a double bond here. You never have a double bond going down to this carbon at the bottom of the structure, so we don't draw any partial occupancy or partial double bond character between that carbon and the carbon above it. And next we have to fill in the partial positive charges. Partial occupancy of positive charge occurs this carbon at the end, so we'll fill in a partial plus symbol there. There's a partial positive charge occupancy in the middle, and at the carbon on the far left. And that is our resonance hybrid structure for that cation. It best represents the real distribution of bonding and charges within that structure. Next, we have this anion. A carbon with a formal charge of -1 will have 2 hydrogens, and it will also have a lone pair. Now, a negative charge repels electrons, so you would never want to draw an arrow pushing electrons towards a negative charge. A negative charge is good at pushing electrons away from it towards other things. And remembering that we can only move pi bonds and lone pairs when drawing additional resonance contributors, we'll move this lone pair towards the pi bonded atom beside it and push those pi bonding electrons up onto the oxygen as a lone pair. Just to keep track of everything, we can draw the lone pairs on the oxygen so that we can keep track of how many electrons will be on that oxygen in the representation of the other resonance contributor. The resulting structure has 3 lone pairs on oxygen, one of those pairs coming from the pair that used to be the bonding pair between the carbon and the oxygen in the pi bond between them. Now, an oxygen with 3 lone pairs and only 1 bond to it has a negative charge as formal charge of -1. Now we have to draw the resonance hybrid for this structure. So again, we begin by sketching out the sigma bond framework, knowing that none of the sigma bonds will move in the 2 representations of the resonance contributors. Now that we've filled out the sigma bond framework, we can assess where there may be partial double bond character. In one of the resonance contributors, we have a double bond between the carbon and oxygen. In the other, we have double bond between the 2 carbons, so we have double bond character in those 2 spots. And then we have to figure out where the partial occupancy of negative charge would be. In one structure, we have an anionic site on oxygen. In the other, we have an anionic site on carbon. So we fill in those two partial negative charges in those two atoms, and that's our resonance hybrid. And now we have our final problem at the bottom of the page. We have a cation in which there's a nitrogen in the structure, and the rest of the atoms forming the sigma bond framework are carbon atoms. And now we have the possibility to move a lone pair on nitrogen, as well as the pi bond that exists in this double bond between carbons. And we're going to have to move electrons towards this positive charge because positive charges attract negative charge towards them. So we can move the pi bond towards that positive charge and draw the next contributor, sketching out the sigma bond framework, and then indicating to which site we've moved the pi bond in between these two carbons on the right. And that leaves this carbon at the top, which used to have a pi bond going to it for its fourth bond. That leaves that carbon with only 3 bonds. So that will have a formal charge of +1. And now we've positioned a positive charge right beside an atom with a lone pair. So now we can draw the lone pair donating towards that positive charge to create another resonance contributor. So the 2 electrons that used to be a lone pair on the nitrogen are now being used to represent the second bond between the nitrogen and the carbon. Now, where did that positive charge go? You have to have charge balance in all of these resonance contributors. Well, you had a nitrogen that was neutral, and it just gave away a share of electrons. And if you figure out the formal charge in this nitrogen, you will see that it is +1. And now all we're left with doing is forming the resonance hybrid. So we'll first sketch out the sigma bond framework, and now we'll figure out where in this molecule you may have partial double bond character. We started off in our first contributor with some multiple bond character in that position. The next contributor we drew, we had some double bond character in that position. And then finally, we pushed electrons around to have some double bond character between the nitrogen and carbon. And then we have to figure out, well, where do we have some occupancy of positive charge? Now we have some partial occupancy here, partial positive. And then we drew a contributor in which we have a partial positive on that carbon, and then some positive charge character on the nitrogen because of the representation in this structure. This problem tests our knowledge of the elementary steps of reaction mechanisms, and it asks us to provide the arrows necessary to effect that transformation, as well as providing the product. The first step they ask us about is electrophilic addition. As the name suggests, we are attempting to add an electrophile to some other species. We first have to identify what is going to serve as the electrophile, and if you see a cation, that's a pretty good electrophile. Now, what's going to provide electrons for that electrophile to allow it to add to the other molecule? And in this case, we don't have any lone pairs, so the pi bond is our only option. We have to donate those to the iodinium cation in that case. And what that's going to give us, but now we've added an iodine to the carbon, normal charge of +1. Next, we're asked to do an electrophilic elimination from that species, and we could eliminate the iodine and go back this way. That would be an example of an electrophilic elimination. And that would be an acceptable answer, but another option would be to eliminate something different, like this proton. And in the electrophilic elimination, you want an electrophile to come off of your molecule with the establishment of a pi bond. In this case, the electrophile eliminated would be a proton, and the pi bond you establish would be between the 2 carbons at the top of this ring. In the second example, we're told to do a heterolysis. Now, you could do a heterolysis of any of these 4 bonds in this molecule, but it specifically wants you to break the carbon-chlorine bond. We're going to break this bond, and it's asking you to make a chloride anion. So, okay, I need to make a chloride anion, which means the chlorine has to go from being neutral to being anionic. It needs to be the atom that accepts electrons, and that's your heterolysis step. The third problem is a carbocation rearrangement. This means that the carbocation, a species with a plus charge on carbon, simply rearranges to a different carbocation. So what we have is a positive charge on this carbon on the right, and remember that the carbocation rearrangement can only occur with movement of the positive charge to a carbon directly beside it. And there's only 1 carbon beside it. We have 2 hydrogens beside it as well. But in a carbocation rearrangement, two bonding electrons on a carbon adjacent to the positively charged carbon will be pulled over to that positively charged site. So the carbon on the left is left with two CH3 units that it started with. It loses that H that used to be attached above it. That H with its two electrons has moved over to the carbon on the right to make a new carbon-hydrogen bond. Now that leaves the carbon on the left with only 3 bonds, no lone pair. So your carbocation has migrated from the carbon on the right to the carbon on the left. Finally, we have nucleophilic addition. In this case, a nucleophile will push electrons towards an atom with a pi bond, and it will push the pi bonding electrons to a different atom. Here we have a nucleophile, something with a negative charge that's easy to identify, and we have to figure out to which atom in the structure those electrons might be donated. You only have 2 atoms that are part of a doubly bound unit, the carbon and the nitrogen, and you need to fill in the partial negative, partial positive of that polar bond and see to which end of that pi bond the nucleophile may be attracted. If we do that, we see that there's a partial positive on the carbon, so you say yes, the electrons will be attracted to that site. And I can't just make a 5th bond to that carbon without pushing some electrons away. The pi bond electrons are going to be pushed up towards that nitrogen. And that leads us to not breaking any of the bonds along that main chain, but pushing a pair of electrons up to the nitrogen. The nitrogen already had a lone pair that we didn't have drawn in. The new bond we made by donating electrons from the nucleophilic H, the hydride, to the carbon is right here. That's your new bond. And the negative charge will be pushed onto the nitrogen, because this is a nitrogen with 2 lone pairs and 2 bonds. If you figure out the formal charge, it's -1. Another type of problem that's pretty common in organic chemistry is you take some compounds and mix them together and a reaction takes place and you can figure out what products you get. And you want to figure out what type of reaction took place, and you want to figure out how do those electrons rearrange to accomplish the transformation. And that's what this problem is testing us on here. So let's look at this first example. We see that in going from starting materials to products, an I- comes off of the molecule. The carbon-iodine bond is going to have to break. A bromine is attached to the carbon in place of the iodine. So we're going to have to establish a new bond here. In addition, the iodine goes from being neutral to being negative, so the iodine must gain electrons. On the other hand, the bromine goes from being negative in the starting materials to neutral in the product. So the bromine has to give up some of its electrons to lose that negative charge. If we then fill in the arrows to accomplish everything we said we needed to do, we need to donate electrons from the bromine to the carbon, and then the electrons that used to be in the carbon-iodine bond have to be given to the iodine, which needs to gain electrons. So we've simultaneously made one sigma bond, the bromine-carbon, while breaking another sigma bond, the carbon-iodine. This is the definition of an SN2 reaction. This second example involves more rearrangements of electrons, and one of the things that can be helpful in these more complicated looking examples is to fill in hydrogen atoms, at least on the carbon atoms that are involved in the reaction. We can see if we number the carbon atom chain that the most obvious change in the carbon chain is that you have a bond between carbons 3 and 4. So I filled in the hydrogens on carbons 3 and 4 to figure out what's going to happen to them. And then we can start to analyze what happens to the rest of the fragments, like this bromine. Well, the bromine is going to come off as an anion. We're going to have to get rid of that bond. And not only that, but the bromine has to become negative in the product, so it's going to have to gain electrons to get that negative charge somewhere. On the other hand, the hydroxide oxygen starts off being negative, but the oxygen ends up being neutral in the water molecule. So you need to make an OH bond, breaking one of those hydrogens off of the carbon. And to become neutral from negative, the oxygen has to give electrons away. Finally, we need to indicate, okay, we need to put 2 electrons in between the carbons 3 and 4 in order to establish that pi bond. Now that we have all those pieces of information in place, we can fill in the arrows needed to accomplish those transformations. So the O- will donate electrons to make the new bond it needs with the proton. the bromine will pull the electrons out of that carbon-bromine bond so that it becomes an anion at the end. And then the last bond we have to break is the hydrogen-carbon bond, and the last bond we need to make is in between the two carbons, right adjacent to that hydrogen. So those three arrows accomplish the transformation we saw. And that type of reaction, where you have a base pulling a proton off of something with the establishment of a double bond and a leaving group coming off, is what we call the E2 reaction. Next, we see ammonia and borane coming together with a new bond established between the two, so we need to put some electrons in this space between the nitrogen and the boron. And we see that the nitrogen needs to become positive, so the nitrogen needs to give electrons away. On the other hand, the boron will become negative in the product from being neutral in the starting material, so it needs to gain electrons. So that's a pretty straightforward step. You just have a donation of electrons from the nitrogen to the boron. This could be described also as a simple Lewis acid-base reaction. We can also call this coordination. Finally, we have this fourth problem, where you start off with a carbocation and you end with a carbocation. So this is pretty easy to recognize as a carbocation rearrangement. And if you take a look at what changes, well, the CH3 group with this pair of electrons is going to have to move over to this area to bond to the carbon on the right. It didn't used to have a CH3 group on it. The carbon on the left has 3 CH3 groups to start. It only has 2 in the product, so that group has to move over. And you simply say, I need to take these 2 electrons out of this bond so that bond's not there anymore, and use them to make a bond to that carbon instead. Just use the arrow to point to that. And that's a carbocation rearrangement. The final practice problem of this set is related to the definitions of acids and bases and how those definitions have evolved over time. 3 of the main types of definitions for acids and bases are the Arrhenius, Bronsted-Lowry, and Lewis definitions. These are the definitions as they are provided in your primer. And another part of this problem not only is to define these different terms, what constitutes an acid or a base under these different definitions, but also to provide a specific example of each of these. It's very easy to think of an Arrhenius acid or an Arrhenius base. Those are the very strong acids and bases. They were probably the first ones we learned. Hydrochloric acid would dissolve in water to make H plus and Cl minus, for example. If an Arrhenius base is something that makes a hydroxide in solution, you just say, well, I need an ionic compound that will dissociate. So a sodium into hydroxide. You've got a metal attached to a nonmetal that would dissociate in water quite readily to form hydroxide and sodium ions. Those are good examples of Arrhenius acids and bases. Now, the definition for a Bronsted-Lowry acid isn't that different from an Arrhenius acid. You could use the exact same example for a Bronsted-Lowry acid as you did for the Arrhenius acid, because certainly the HCl, hydrochloric acid, would donate an H plus in solution. The definition for a Bronsted-Lowry base is a little bit different. It's a proton acceptor. Now, certainly anything that would have a hydroxide in solution would accept a proton to form water, classic neutralization reaction. But other things can be proton acceptors as well, other than hydroxide. And that's what differentiates the Bronsted-Lowry definitions from the Arrhenius definition. Let's consider ammonia, for example. Scientists recognized that if they added ammonia to a solution that used to be acidic, it would become neutral or even basic, depending on how much ammonia you added. And they figured out that this is because ammonia can donate a pair of electrons to that H, that proton, and then you'll have an ammonium salt. So in this definition, the ammonia could also serve as a base under the Bronsted-Lowry definition because it accepts a proton to form some new species. The broadest definitions of acids and bases presented in your primer are the Lewis definitions. In this case, an acid doesn't have to be an H+. Could be. It's accepting a pair of electrons here. But it could be anything else that accepts an electron pair as well. In the prior problem, we had borane, for example, reacting with ammonia and doing a coordination, or a Lewis acid type reaction, where a lone pair was donated from the ammonia to the borane. And in this case, you have a Lewis acid the acceptor of the lone pair, and you have a Lewis base that is the donor of the lone pair.